Hello everyone, I am Professor Lee from the Communication Engineering Teaching and Research section at Wuzhou University. Welcome you to this mini lecture. Today we will cover Chapter 2, Section 4, the basic operations on discrete signals. The basic operations on discrete signals mainly include the following items. First, time reversal. A discrete signal is transformed from f of k to f of minus k. That is, f of k is flipped by 180 degrees about the vertical axis. A graphical example is shown below. The figure shows the time reversal process of the discrete signal f of k. Each point from k to f of k in f of k is flipped about the vertical axis to from minus k to f of k, i.e., the k value changes sign, while f of k remains unchanged. From the reversal result, we observe, for the original signal f of k, in increasing order along the k-axis, the values 1, 2, 3, 2 correspond to k equals minus 1, 0, 1, 2. After reversal, for f of minus k, a symmetric pattern appears along the k-axis. The values 2, 3, 2, 1 correspond to k equals minus 2, minus 1, 0, 1. In summary, the reversal operation has these features. 1. Symmetry. The reverse signal f of minus k is the mirror image of f of k about the vertical axis. 2. Value invariance. The signal values f of k remain unchanged during reversal. Second, shifting. A discrete signal is transformed from f of k to f of k plus or minus n, assuming n greater than 0. f of k plus n denotes shifting f of k left by n samples, and f of k minus n denotes shifting f of k right by n samples. The illustrated plot shows the discrete signal f of k in the left and right shifted signals f of k plus 2 and f of k minus 2, respectively. Third, scaling. We first introduce decimation, which transforms the original sequence f of k into a new sequence f of mk by selecting one sample every m samples, where m is a positive integer. In the example, given f of k, we draw the k sum equals 2, namely f of 2k. The points at k equals 0, 1, 2, 3, 4 are compressed by 1/2 to 0, 0.51, 1.52. However, in a discrete sequence, k must be integer valued, so the fractional indices are discarded, and only k equals 0, 1, 2 remain while the other points are removed. That is, the original sequence f of k is downsampled by taking every other sample to form f of 2k. Consequently, after decimation, the new sequence f of mk contains fewer points and a larger space in between adjacent points, effectively shortening the sequence, which is suitable for downsampling in signal processing. We now introduce interpolation within scaling, which transforms f of k into f of k over m. Values are kept only at k that are integer multiples of m, and all other k are set to 0. In other words, new samples are inserted between the original samples, thereby changing the sequence of scale. In the two plots below, m equals 2, i.e. f of k is transformed into f of k divided by 2. The original sample indices are 0, 1, and 2. After scaling, the non-zero samples occur at indices 0, 2, and 4, with all intermediate indices filled with 0. That is, one sample is inserted between every two adjacent original samples, achieving a refined sequence. We can conclude that interpolation inserts m-1 samples between any two adjacent samples, yielding a new, denser sequence suitable for applications requiring higher resolution or finer representations. Sequence addition means adding the values of several discrete sequences at the same index. The expression is shown in the figure. In the example, f1 of k equals minus 1 for k from negative infinity to minus 1, and equals 1 for k from 0 to positive infinity. Adding f1 of k to f2 of k, which equals 1 for all k from negative infinity to positive infinity, and summing value by value at the same indices, We finally obtain a discrete sequence whose value equals 2 for k from 0 to infinity. Sequence multiplication means multiplying the values of several discrete sequences at the same index. The expression is shown in the figure. In the example, f1 of k equals 1 for indices from -1 to 1, multiplying it by the corresponding values of f2 of k, defined over -3 to 3. We multiply the values at matching indices and obtain the resulting sequence shown below. We now introduce differences, finite differences, which include the forward difference and the backward difference. We first present the first and second order expressions, and finally summarize the nth order difference expression. The first order backward difference uses f of k to get to its one sample right shift f of k minus 1. Each increase in order adds one more one sample right shift. The forward difference works similarly. The only distinction is that with each increase in order, you add a discrete sequence shifted one unit to the left. The unit impulse sequence can also be expressed as the difference of unit step sequences. In continuous time signals, the impulse signal equals the derivative of the step signal, which is akin to increasing the order by 1. In discrete time, this relationship is represented using finite differences. The formulas listed in the figure are commonly used difference operations in discrete signal processing that are used to analyze trends of change in signals. The unit impulse sequence can be expressed as a difference of unit step sequences, and the formula represents the instantaneous change at index k. Finally, we introduce the last basic operation, summation. The expression is y of k equal to the cumulative sum of f of n from n equals -infinity up to k. The unit step sequence can be expressed as the summation of unit impulse sequences. The formula is shown in the figure. Finally, please reflect on this lesson and complete the following exercises, which are intended to consolidate today's key points and further deepen your understanding. That concludes this mini lecture. See you in the next class.